Okay, the simulation is complete. Let's check the S parameter. Here you can see that S parameter is below minus 10 dB at around 1.56. So let's zoom that, and at 1.566 it is less than minus 10 dB, and let's check the axial ratio. Okay, so here you can see that axial ratio is less than 3 dB. So here you can see that it is showing at 1.57 it is showing 1.98. So if the axial ratio is less than 3 dB, we know that we can consider it as a circular polarization. To see that in far field, let's see how you can interpret from that far field also. So I'm going to take this frequency at 1.57 where the axial ratio is 1.98, which is less than 3 dB. So maybe we can say that this antenna is working as a circularly polarized antenna from 1.56 to 1.575. So this range where axial ratio is less than 3 dB. So the frequency is 1.57. So let's see how we can interpret that from the far field. So this far field is like this because we are seeing the far field at some frequency. So to see the far field at 1.57 where the axial ratio is 1.88, okay, 1.57. So you can go to the far field and click on the properties. So now the far field you are seeing is for 2.9. So we have to see the far field for 1.57. Okay, so click apply. So you can see that this is the far field result. So it is showing the gain of around 6.56. So it is very good because here you can see that the gain is around 6.56 and the directivity is around 7. So there is not much difference between the directivity and the gain. That is because we are using the Rogers RT Duroid substrate. It has a very low loss. Because of that, the radiation loss is very less. That is why we are seeing the directivity and gain almost similar. But in case of our previous rectangular patch antenna simulations, we have seen that there will be huge difference between the gain and directivity if we are using the low C substrate like FR4. So here you can see this is how your far field is looking like. Okay. So now our purpose is we have to see the far field because we have to make sure that our EX and EY result has to be the same. So EX and EY, to see the EX and EY result, we know that if we cut this along the phi 0 plane and phi 90 plane, we will be getting the result in X and Y component. So you can go to 1D result, and this is the phi 0 result. So we have to see that in Cartesian. Okay, so if you go here and choose these options, you can see the complete field here. Phi 0. Okay. So now we have to make sure that both phi 0 and phi 90, that is EX and EY component in far field have almost same result. So let's go for that because if I need to compare both here, maybe we can create a folder inside the 1D result. I'm going to name it as far field at 1.57 gigahertz, and I'm going to use so far field phi 0. I'm going to copy. If you click it here and Control C, it will copy here. So this is going to be our phi 0. So I'm going to rename it as phi 0 degree. So let's go again here and again here, and we can select the phi 90, and we can copy and we can paste it here. So this is 5. I'm going to rename it as 590°. So here you can see that both are almost same. So at phi equal to 0° means at theta equal to 0°, you can see that both have the same magnitude. That means that both co and cross polar values are same. That is what is meant by axial ratio. So it means that axial ratio is okay, as we are obtaining both co and cross polarization almost similar. That is what is indicated here. So this value, axial ratio. So from here to here you can obtain the circular polarization. So to obtain, because we can also see the circular polarization using the surface current and the electric field information. Let's go for that. So for that, for the field monitor, click on new field monitor, electric field. So it is 1.57. Oh, sorry, it's gone. 1.57. Click apply. H field also. Click OK. 1, not 1. Do you want to? Yes. So E field 1.57. H field. Okay, I'm going to select automatic because I need to know what is this frequency. So apply E field. Okay. Oh, where is it? H field 1.57. Okay. So we have the electric field, magnetic field, and far field. Then you can just start the simulation. Okay, simulation is complete. Let's see the surface current distribution. So select view front. So I'm going to select the patch. So select the patch and we can see how the surface current is. Click on surface current. So here you can see that how the surface current distribution is. By dragging this you can change the value. So I am just going to show you how we can see that how the surface current is varying. So first one, because in most of the publications you will be seeing the surface current at different phases, so you can change the phase here, phase 45°. So now you can see that the arrow direction is changed in this direction. Then go for 90°, so it is changed in this direction. Then 135°, so it is now vertical. Then 180°, so now it is in the opposite direction. Then 225°, it is going on the horizontal other direction. Then 270, so it is getting rotated. Then 325, so it is getting again rotated. And 360. So here you can see that how the rotation is happening. So if you consider the case, we can see that the rotation, like the rotation is happening like this. It is happening like this thing. Like maybe I will draw with a pen. So it is happening like this one. So if we use our right hand with thumb pointing away from the patch antenna, and if you observe this folding of the thumb, you can see that the direction of the folding and the rotation of the arrow is same. So here the folding is in this direction, and the rotation of the arrow is also in the direction with respect to the change in phase. That means that this is an RHCP, right hand circularly polarized. This is how we can observe where our antenna is right hand or left hand circularly polarized. So maybe I will use the animate field. Here you can see that how this rotation is happening. So maybe if you use the properties, you can change the speed, go for animation and animation rate. So now you can see clearly how the rotation is happening. So this is how we are saying that it is a right hand circularly polarized antenna. So now we got that. Okay, so I may close this thing. So if we are designing an antenna with truncation at this position, we will get a right hand circularly polarized antenna. So maybe I will also show you if we rotate this thing, how you can obtain a left hand circularly polarization. Okay, so this is our simulated antenna. So I have saved that the same file. So this same antenna I have renamed and save it as LHCP. So now our purpose is I am going to rotate this one along this thing. So we can obtain left hand circular polarization. So rotate. So I'm going to rotate, sorry, 90. So if you rotate by 90, so with this antenna, you have to obtain the left-hand circular polarization. So let's see that. So start simulation. Okay, the simulation is complete. So my main interest is to see the surface current. Okay, I have to check. So let's see how the field is rotating. Here you can see that the field is rotating in the other direction. So you can see how it is rotating. So maybe we can change the animation speed a little bit slow. So here you can see that it is rotating in this direction, but in case of RHCP it was rotating in the opposite direction. Okay. Okay, I have to check only the patch. Animate field. So here you can see that it's in this direction, and in case of LHCP it is in the opposite direction. So if you put your left hand with all the fingers folded, you can see that the folding of your fingers is in the same direction of this rotation. That is, put your left hand on the same plane as that of the antenna with thumb pointing out, then you can see that all your fingers will be folded in this same direction. So this is a left hand circularly polarized antenna. This is a right hand circularly polarized antenna. So in this case, if you have to put the figures on this publications, you can check 0 like this, and for different phase you can see the phase, and you can say that the rotation is in this left hand direction. That is why this is an LHCP antenna. That's how we are doing or defining RHCP and LHCP from the simulations. I hope you get some idea about that. So here I have put our patch antenna just to show you how the surface current will be, because in our case we have seen how the surface current, because we can clearly see the rotation in that LHCP, but in this case, so this is a linearly polarized antenna, just the patch antenna. So it is just a patch antenna, no truncation. Here you can see that field is only changing along the y direction. That is why this is a linearly polarized antenna along the y direction. But in the case of LHCP and RHCP, you can see that it has X and Y components and it is creating circularly polarization. I hope you get some idea about circular polarization and linear polarization and how you can calculate the axial ratio and which post-processing has to be set to get the axial ratio. Thank you.